So you're ready to dive into the world of quantum programming. Awesome, you're in exactly the right place. Today we're going to get our hands on Qiskit, which is the leading open source framework that actually lets you build and run your own quantum algorithms. So let's get right into it. So here's our game plan. We're going to walk through 6 key steps that will take you from zero to running your very first quantum program. We'll kick things off with what Qiskit even is, then get your computer all set up, understanding the real building blocks of a circuit, then write some code, run it, and finally take a look at where you can go from here. All right. First things first, before we can write a single line of code, we need to get a handle on this thing we're using. What exactly is Qiskit? What's really cool about this is the scope. Qiskit, which was built by IBM and runs on Python, isn't just one single tool. It's actually a whole suite of them. Think of it as a bridge that connects the theoretical algorithms you read about to actual quantum hardware that you can program and access right through the cloud. So theory is great and all, but let's be real, we're here to get our hands dirty. So the first practical step is to get your own quantum development environment all set up and ready to go. Getting started is surprisingly simple. First, you make sure you have a recent version of Python. Then, trust me on this, it's a best practice for any Python project. Create a virtual environment. It just keeps everything from your project nice and tidy. Once it's activated, a quick pip install Qiskit does pretty much all the heavy lifting. Oh, and I would definitely run that second command to add visualizing support. That's the part that lets you draw out those really cool circuit diagrams we're about to see. With our tools already, it's time to get to know the fundamental unit of any quantum program, the quantum circuit itself. The best way to think of a quantum circuit is like a recipe. It's a set of instructions for your quantum computer. You start off with your ingredients, which are the qubits, then you apply a series of operations called quantum gates to change them. And in these diagrams, time always flows from left to right. So inside every circuit, you're going to have to find 2 types of registers. First, you have the quantum registers. This is where all the cool quantum magic happens. They hold the qubits that can be in superposition and get entangled. Then you have the classical registers. They're more for storage. When you measure a qubit, it collapses down to a simple 0 or 1, and that result gets stored in a classical register. Just like classical computers have their basic AND or gates, quantum computers have their own set. And for our first program, we really only need 2. First is the Hadamard gate or the H gate. This is your key to superposition. It takes a qubit that's a definite 0 1 and puts it into a state that's a mix of both at the same time. Then you have the CNOT gate. This one needs 2 qubits, and it's how we create entanglement. That mind-bending property where 2 qubits become linked. And what happens to one instantly affects the other. So this is it. We have the pieces. Let's put them together and write our very first quantum program. In the classical world, the first program is always hello world. Well, in quantum computing, it's creating something called a Bell state, which is the perfect state of maximum entanglement between 2 qubits. And check this out, it's surprisingly simple. Let's just walk through this code together. First, we import the tools we need. Then we create a quantum circuit with 2 quantum bits and 2 classical bits. Now for the fun part, we apply a Hadamard gate. That's the H to the first qubit. And boom, you have superposition. Then we apply the CNOT gate, the CX, which links the first qubit to the second one. And that's it, entanglement. Finally, we tell it to measure both qubits, then we draw the circuit. And that diagram at the bottom, that right there is our very first quantum program. We built the circuit. That's awesome. But how do we actually run it? How do we get a result? This is where we go from just drawing on a screen to an actual computation. Now here's the super important step that happens behind the scenes. You can't just send any circuit to any quantum computer. Every piece of hardware is different. It has its own quirks, its own limitations, like which qubits can talk to each other. So this process is called transpilation, which is basically a translation step. Qiskit takes our ideal circuit and automatically rewrites it, optimizing it so it can run perfectly on the specific hardware we choose. So when you're ready to execute your circuit, you basically have 2 options. You can use a simulator, which just runs on your regular laptop. This is perfect when you're learning because it gives you a perfect noise-free result every single time. Or this is the really exciting part. You can send your circuit to actual quantum hardware over the cloud. This lets you see the effects of a real quantum noise, which is a massive part of the challenge in the whole field. Now, to make this whole interaction a bit easier, Qiskit gives us something called primitives. They're basically a way to focus on the tasks you want to accomplish. You've got the sampler, which is what you use when you just want the raw measurement outcomes, the counts of zeros and ones. Then you have the estimator, which is for more advanced tasks, calculating the average value of some property of your system. This is the absolute core to a lot of big quantum algorithms. So you've done it. You've built and run your first quantum circuit. That's a huge step. But what's next? This is the beginning of your journey. This workflow right here shows the whole shebang. the little circuit we just built, that fits right into the circuit design and translation box. But as you can see, the real project is a whole cycle. It's about defining a problem, processing the results, sometimes feeding them back to refine your approach, and then validating everything. It's a whole development process. And the cool thing is, where you go from here is totally up to you. It's kind of like choose your own adventure. You could dive into implementing famous algorithms like V2E for chemistry, or maybe Shor's algorithm for factoring. You could explore the Qiskit libraries for finance or machine learning, or maybe even get fascinated by the hardware you want to learn how to fight back against noise. More importantly, I'd say just dive into documentation and join the community. There are tons of people out there learning this stuff. So we'll leave you with this question. You've now got the fundamental tools to program a quantum computer. With just a few lines of code, you create a superposition entanglement. That's incredible. The real question is, what problem, big or small, are you going to try to solve next? That's up to you to answer. Thank you for tuning into another episode of Quantlock. Hope you all have a great day.